First, I made a goof in what I said to you yesterday about the way by which structures are drawn in organic chemistry class. So let me try to get that fixed right now. When we drew a picture for toluene, I showed you sticks at each carbon atom corner of this six-membered ring, representing a bond to hydrogen. That's correct. But in organic chemistry class, they don't do this. They will show a benzene ring like this, toluene molecule like this, no sticks. Because in organic chemistry class, which is what I forgot, and this is the goof I made yesterday, a stick represents a bond to a methyl group. Because methyl groups are very, very commonly encountered peripheral groups for organic molecules. So I did this for our convenience to indicate with this, if you take it, that's an H atom at the end of each stick, we don't have to take time to draw the H's. But the organic folks don't do that. They'll draw just like this and expect you to recognize that each one of these carbon atoms is an sp2 carbon, which means it's got to have a hydrogen atom connected to it, which is implied, given that hydrogen atom is the most common peripheral atom by far. If there's any kind of peripheral atom for an organic molecule other than hydrogen, they draw that. But hydrogen atoms, they don't draw that. That's perhaps a better example of what I wish to say. They usually draw, or pardon me, often draw organic molecules with these line drawings. See this formula? H3C, CH2, CH2, CH3. That's straight chain butane. 1 butane or N-butane for normal. In organic class, rather than taking time to write all of this stuff, I can represent this molecule by this picture. Because this means a CH2 group, sp3 carbon, CH2 group, sp3 carbon, a CH3 group, because that's at the end of the stick, and a CH3 group. So I can do all of this just like that. That's pretty fast. It's something I should have thought to put in the writing of assignment 6 for the present 45L lab manual, where we asked you to learn about Lewis structures and how to draw pictures of models and molecules to get geometric perspective and things like that. I'm now working on the rewrite, the latest rewrite of the 45L lab book, and it's my intention to include this. So, if you still have, or if you still are confused about this, please ask so we can get this straightened out. And so we proceed with the tail end of chapter 17. And now take a look at a very important example of how to solve challenging equilibrium problems. We will, in chapter 18, which is where we're headed. In fact, many of you have already been in discussion class and had some introductory conversation on chapter 18. Bronsted-Lowry acid-base chemistry. In that chapter, we will learn how to do detailed analyses of all sorts of Bronsted-Lowry acid-base involved aqueous equilibrium systems. In fact, we will show you, with the work we do in chapter 18, how You can take any water solution, and analyze it in sufficient detail so as to be able to determine the correct concentration of each and every species in the solution whose existence depends on pH. And most species in water solution have an existence that depend on pH. Some don't, but most do. That's pretty important. Biochemistry folks often have to consider such things because biochemistry is in essence a particular discipline regarding the study of molecules of nature and life. And I think you'll accept my statement, which I already made to you and will now repeat, that water is by far the most important solvent regarding life systems on Earth. Blood, sweat, tears. Hey. And if, for example, you wish to be a forensic chemist, where trace amounts of materials can be toxic to the human system, trace amounts, it might be necessary to get a concentration handle on these trace amounts. Well, with the arithmetic and analyses that we'll show you how to perform in Chapter 18, you'll be able to do this for any water system after we get done with what we are going to do. But as I said, this detailed analysis will involve us on a regular basis in dealing with some particularly complex aqueous equilibrium systems. Now, the analysis we're now going to do is now not for an aqueous equilibrium, but it will be an illustration of how to go about tackling difficult, challenging problems regarding equilibrium analysis. Let's take a look again at this reaction which we looked at previously from the other direction. Doesn't make any difference. If we were to study this reaction at a set of conditions for which the equilibrium constant value was something other than 1. Let's imagine just for a moment that I study this under conditions for which this K value is 10. And then I want to write the equilibrium reaction in the opposite direction, because for an equilibrium system, the reactions are going both ways. In fact, practically speaking, for any chemical system, reactions are going both ways. They just happen to be going at the same rate when it's at equilibrium. If the equilibrium constant for this reaction studied at a particular set of conditions is 10, and I choose to write the equation in the opposite direction, what will be the value for the equilibrium constant? 1 over 10. We just invert the K value, that's all. Because I'd invert the equilibrium constant expression, then I'd invert the K value. Now, if I have the convenience of studying this at conditions for which the observed equilibrium constant, the measured equilibrium constant is 1, then of course if I write any other direction, the equilibrium constant value is still going to be 1. But that applies only when the equilibrium constant value is 1. But as I said, even though this is going to be an illustration of detailed problem solving for equilibrium systems, I want to keep the numbers part as simple as possible so you can appreciate the chemistry. And after you appreciate the chemistry, then we can make the numbers more challenging, as exhibited by just about any real chemical system. So let's imagine we're studying this equilibrium, which in this case represents the decomposition of ammonia. Here's the equilibrium constant expression. We're imagining to study this at conditions for which we have the very convenient equilibrium constant value of 1.0, and we're going to study this system inside a piston cylinder apparatus. Initially, we're imagining this system exists. The equilibrium exists, nitrogen, hydrogen, ammonia, each present in a piston cylinder gadget operated at an external pressure of 1 atmosphere, which is usually about what atmospheric pressure actually is. And the internal volume of the cylinder is 1.0 liters. So if all this is true, and I find that the nitrogen molarity and hydrogen molarities are equal and they're each equal to 1.0, what's the ammonia molarity? What is it? 1.0. Can't be anything but. So, again, as things stand, the numbers are very simple. Couldn't be simpler. Now I'm going to make a change on the system. I'm going to take a hold on the handle of the piston, the handle on the piston, and squeeze in. Of course, nitrogen, hydrogen, and ammonia are still present. But now, I've reduced the volume occupied by the system, to 0.50 liters. Well, that's what we did. And then I'm going to lock the piston in place. Did the change which I apply, at the instant at which I applied this change, did that upset the equilibrium? Yes. Sure did. We talked about cases like this yesterday. Well then, since I haven't added or subtracted anything from the composition and contents of the system, we now ask the question, what reaction, forward as written or reverse as written, has got to occur to get us back to equilibrium? Let's have a vote. Remember, I expect you to vote. Reverse reaction occurs to get us back to equilibrium. Most are voting correctly. As we said yesterday, if you look at a reaction which is strictly gas phase, and you apply pressure to the system, that's the only change applied to the system. You can recognize that on increasing the pressure, from a gee whiz generalization standpoint, you can recognize that the reaction system is going to proceed from more moles to fewer moles. Well, based on the coefficients, we're seeing more moles product compared to moles reactants. Because as I go this way, I am in fact reducing the number of particles in the system. Because every time I make 2 ammonia molecules, I must do so at the expense of consuming 1 nitrogen molecule and 3 hydrogen molecules. Nothing fancy about that. All we're doing is letting that reaction equation talk to us. Conversely, if I reduce the pressure and let the system now occupy a larger volume, then we're going to travel from fewer moles to more moles. So that would encourage this reaction to get us back to equilibrium, to go as written, left to right. Now perhaps, or I shouldn't say perhaps, but I hope by now you've recognized that there's an arithmetic consideration which applies to this. It's in the notes. On page 17.8, it's called reaction quotient. How many of you have seen this? You're reading, you're doing what I ask you to do? Reaction quotient. What's a reaction quotient? It's an equation, an expression for a reaction system which has exactly the same form as the equilibrium constant expression. So from a chemistry standpoint, if you can write an equilibrium constant for a reaction system, then at the same time you've written the Q expression, the reaction quotient. What's the difference? For reaction quotient, any set of conditions are imaginable. But for equilibrium, we can have exclusively equilibrium concentrations if we're dealing with a system in which only concentrations are involved. Equilibrium partial pressures if gases are involved. Now these are gases, but since all the analyses, as I mentioned yesterday, all the analyses we're going to do in Chapter 18 will involve water solutions, I want us to get in the habit right now of dealing with equilibria that are expressed in terms of molar concentrations, because that's all we're going to do in Chapter 18. When we get further on down the line, we'll go back and take a look at some Kp equilibrium constant expressions. And then we'll look at equilibrium constant expressions which are neither Kp or Kc, because they got concentrations in them as well as partial pressures, because the reaction system involves solution, species, solutes. And therefore, the equilibrium will depend on the concentrations of these solutes. And it will also involve gases. So you can't label that Kc or Kp, because it's a mix of both. For this system, given that the reaction quotient has exactly the same form as the equilibrium constant, there's Q. But what did we do to concentrations when we applied this change? Well, we recognize that from a mole count standpoint, we have initially 1.0 moles of each component of this system. But when we reduce the volume to 0.50 liters, now the concentrations have all doubled. So I put in 2 for the concentrations in Q to find out that Q is equal to 4. Question: if Q greater than K, what reaction occurs in the system to get us back to equilibrium? Reverse. But if K greater than Q, then left to right is written, and if these terms are equal, then we're at AQ. And no net reaction will occur in the system. Well, we looked at this from recognizing that application of pressure to reduce the volume will force the reaction to go from more moles to fewer moles, and with the Q analysis we've reached the same conclusion as we must. So we now know, on getting back to equilibrium, total moles nitrogen, total moles hydrogen will get reduced. And total moles ammonia will get increased. Okay, so far? Now we got to do some algebra. How shall we represent algebraically moles of nitrogen at equilibrium? We started with 1.0 moles, just like we started 1.0 moles of the other system components. Here's what we know so far. Moles of this increase, moles of this decrease, moles of this decrease. Directive. When you play the algebra game for analyzing any equilibrium system like this, let the equation for the reaction be your algebra guide. Nothing could be more straightforward. The equation for the reaction is written, says, if by this reaction I'm going to make 2 moles of ammonia, I got to use up 1 mole of nitrogen. Okay? So let's imagine that I'm going to say the quantity of nitrogen which disappears is our wonderful, most common unknown representative, at least that's my bet, X. X marks the spot. All right? Well, if in getting back to equilibrium we use up X moles nitrogen, how many moles of hydrogen must we use? 3X. Bingo. The 3 up there as the multiplier on hydrogen tells us. Correspondingly, on using up X moles of nitrogen and 3X moles of hydrogen, how many moles of ammonia will we make? 2X. Wonderful. All we did was to let that reaction equation be our algebra guide. However, now we see some arithmetic complexity as a consequence of changing the volume. Because when we have the volume at some value other than 1.0 liters exactly, then molar concentrations and total moles are hardly equal. And the equilibrium constant expression deals with concentrations, involves concentrations, rests on concentrations. So we can't operate arithmetically with that equilibrium constant expression using these quantities, because these are mole quantities. So let's convert these mole quantities to concentrations. Now then, that means I'm going to take each one of these numbers and divide by 0.50 from an arithmetic standpoint. What do I do to a quantity when I divide it by 0.50? I double it. You agree with that?
Yes.
1 divided by 0.50 is 2. Nothing fancy about this. Simple arithmetic. So, in my mind's eye, I'm going to divide this by 0.50 and get 2.0. The coefficient on x is 1. And there's my concentration for nitrogen. 1.0 minus 3x. That gives me 2.0 minus 6.0x. And 1.0 plus 2x gives me 2.0 plus 4.0x. Now all we've done is some very simple arithmetic. Now then, let's take a look at the fun part. Since we finish with this, I'll get this out of the way. And rewrite K, because the value for the equilibrium constant, so long as we don't change temperature, and so long as we don't deal with gases which will show distinctly non-ideal behavior at a particular temperature, a value for K will remain constant. Well, we didn't make any temperature change. And we're going to imagine that we're operating at a temperature at which the least ideal of the components of this system will behave in accord with PV equals nRT. Which is that component? Which component of this system shows least ideal behavior in behaving as a gas?
Ammonia.
Ammonia. Do you agree with that? Why do you agree with that? I don't want you to agree with anything that I say unless you can back it up. You know that ammonia is a hydrogen bonder? But nitrogen and hydrogen are strictly homonuclear diatomic molecules, and the only types of interparticle attraction forces which such molecules can exhibit are what? Nonpolar molecules. What kinds of attraction forces do they show for each other among and between? Van der Waals, or equivalent term, London. Okay? Well, from an algebra standpoint, we now have all the concentrations which fit into our equilibrium constant expression. And since we've used this, I'll take this out of the way. And now ask, for this problem, the $64 question. How are you going to solve this? Will you expand it? Will you multiply it out? Do you like to deal with algebra puzzles that have the unknown quantity, in this case represented by x, raised to the 4th power? You don't have a magic recipe to deal with that stuff, do you? And you'll find out when we get to acid-base chemistry, where if you have a so-called second-order equation, you can often crack it with the quadratic formula, correct? You know how often I'm going to use the quadratic formula? Never! Because it stands in the way of understanding chemistry, and I won't allow that in this place. And what you will also see, if you pay attention and learn what we're offering, is that you can do it a hell of a lot better and quicker without that clumsy recipe. Just like this problem, for which there is no recipe. So what do you got to rely on? You got to rely on horse sense to solve this. So that's what this issue in the main is about. How do I use my arithmetic horse sense to solve an expression like this? So we're going to ask a question. Which term in K is smallest? There's the first question. There it is. Which of these terms is smallest? This is the nitrogen molarity, this is the hydrogen molarity, this is the ammonia molarity. Which term is smallest? You agree it's the hydrogen molarity? Are you mystified by this? Because I'll bet, until this very moment, that few of you, at most, have made the practice of letting equations like this, arithmetic equations, talk to you. Well, now you got to let these things talk to you. That means you got to let these things tell you what they mean. And then you'll be able to do the arithmetic while understanding and appreciating the arithmetic, which means you'll do the arithmetic as quickly as it can possibly be done. And that's what we want. All right? Each starts out at 2.0 for the three terms contained in our K expression as it is presently written. And from 2.0, in one case we're going to add, and the other two cases we're going to subtract. And what we add or subtract, can these be imaginary numbers?
No.
Can they be negative numbers? Am I going to react a negative quantity of nitrogen and hydrogen to make ammonia? Nope. We're talking about real materials here. Do concentrations have negative values? Can I have a molarity of minus anything? Hell no. How tall is Joe? Negative 12. What the hell are you talking about? A statement like that has no meaning. So we recognized that the H2 molarity is smallest. So we're going to ask another question. Max value for X is. Fill in the blank. Now, in answering this, recognize the significant figure limitation that you have for this calculation. What is the significant figure limitation? How many sig figs? 2. The K expression is to 2. That's it. The molarities, as we have chosen to write them, are to 2 sig figs. So whatever the maximum value is for X, it is not to be expressed beyond 2 sig figs. Okay? I'm listening. I want a maximum value for X. Come on. I heard 0.33. Now, How many of you would like to support the contention of 0.33? How many of you have a different value to put forward? How many of you are totally puzzled? You don't know what the hell's going on at all at this stage of the game. Because you see, we can't answer this question if we're in algebra class. But we are not in algebra class. We're in chemistry class. And I want you to realize that whatever is the value for x, when you put in that value to get the hydrogen molarity, 6 times x cannot be a number which subtracts from 2.0 and sets 2.0 equal to 0 or something minus, can it? Because then we'd have a resulting equilibrium molarity of hydrogen which is negative. What the hell does that mean? It means nothing. It means nonsense. So now, would you like to reconsider, those of you who didn't support the contention of 0.33? Because that's the max value for x. It can't be bigger than 0.33. Because any value bigger than 0.33 on multiplication by 6 and subtraction from 2.0 creates a negative number. And that ain't flying. Are we okay with this? Wonderful. Nothing fancy about it. We're not doing it. We're just recognizing this is chemistry. We're talking about actual material. How much do you weigh? -2. What the hell are you talking about? All right, now here's a directive. To begin solving, speculate on an x value which is easy to handle arithmetically. Given that, we now know that x is equal to or less than 0.33 but greater than 0. You agree with that? So whatever is the value for x, it's something contained in this box. What's the box? 0.010, 0.011, 0.012, all the way till I get to 0.33. It's in there someplace.
Wouldn't it just be less than 0.33? Because if you put in 0.033 into the equation, it would come out with 0.
Well, I didn't say x is 0.33. I'm only saying x is a number which is 0.33 or smaller.
Something about your notation on the board.
Did I have a wrong notation?
Yeah, if x is less than or equal to, if there's no way.
Yeah. X has got to be equal to or less than 0.33.
But if it's equal to, then that says that we have a 0 concentration of hydrogen, which is impossible because we know we have it in this.
All right.
So she's saying.
But if because when you play this significant figure game, okay, you've got to do your arithmetic. Do you remember this in 2045? When I finish this calculation, how many significant figures do I have to wind up with? 2. But how many significant figures do I can keep as I go through the arithmetic to get that answer?
More than 2.
How many? How many? You didn't do this in 2045? How many? 3. Now then, let's look at this directive. Anybody want to suggest a value? A speculation value for x, which is easy to deal with arithmetically. I'm listening. Because what I'm trying to do now is to program you to play this game, because you're going to play this game many, many times during the term. This is your first look-see. 0.1?
0.
0.10. How about that? Yeah, I know, you people like to chip away these significant figures. But you came up with a reasonable suggestion, so I won't penalize you too much. All right? So for this, I'm going to write this down. Try x equals this. All right? Now then, what does this term become if I'm trying x at a value of 0.10? Well, watch out, this is really tough. 2.0 minus 0.2, that's 1.8. 2.0 minus 0.6, that's 1.4. And 2.0 plus 0.4. Boy, that was really hard. Now then, you'll see at this point is when your push button gadgets become quite handy. Anybody got one of these push button gadgets? Go ahead, push the button, see what you get. Let's go, quick and fast. Brrr. I mean, if you can text like crazy, you ought to be able to do this like crazy. What'd you get? I got a value of 0.86. Anybody want to confirm that? You happy with this? Well, I'm saying, is this the result of this arithmetic? This is the result of this arithmetic. All right, so we got a value for Q, because Q is not K until this term is equal to what? 1.0. Thank you. 0.86. Well, that's smaller than K. So what do I now know about the true value for x? Is it larger a little bit or smaller a little bit than 0.10? You seem mystified by this, many of you, because you've been looking at these damned arithmetic statements all this time and you haven't thought about what they mean. I'll bet you went through high school math class pushing buttons on calculators all over the place. And I'm telling you what, if I could get the job that Secretary of Education for this country presently has, Arnie, I forget his last name, for President Obama, things would change, and they'd change damn fast. Because I'd go into every high school math class and grade school math class, and I'd find out every teacher, quote unquote, who's having students use calculators. And I'd horsewhip the SOB in public. And then I'd say, the next time you do this, I'm going to lynch you because you're causing America to be stupid, and I won't stand for that. And I mean it. I'm not kidding about that. Our language is two parts, damn it. Alphanumeric, numbers and letters. And you people have been programmed out of using the numbers part. You can't speak the numbers part. It's not your fault. It's not your fault at all. Well, here's where we're going to try to right that ship. I'm telling you what, math teachers, not math teachers at all when they do that stuff. It's the damn machine doing the arithmetic then, not you. And I won't have that. Because you're the ones that need to understand what these numbers mean. You're the ones that got to put to use this best calculator that you'll ever have. And get it past this math fog which you've created in your noggin. Because you do even the simplest arithmetic with that push button device. I can tell you tons of stories about this. Student in my class a couple years ago couldn't divide 3.5 by 7. And I said, what's 35 divided by 7? 5. So I said, what's 3.5 divided by 7? Petrified. Just because of that damn decimal point. She says, can I have scratch paper? I gave her the scratch paper. 20 minutes later, this student was in absolute tears with scribbles all over hell without showing the answer of 0.5 ever. This is the kind of stuff your mind has been messed up to become. And we're going to take away that mess up. At least we're going to make a serious effort to do that. I don't want that crap. I don't want that junk at all. I want your minds to be sharp and clear, not fogged up with this inability to communicate in science class. Every damn thing in science depends on measurement. You're dealing with numbers all the time. Numbers which have units. You have to respect this stuff. And in order to be able to respect it, you have to understand it. All right? So the true value for x has got to compare how to this? Look at this expression. Depending on the value for x, or put it this way, as x gets larger, what happens to the terms in the numerator? Do they get bigger or smaller? And this term gets larger as x gets larger. And we've already got a value for this term which is smaller than k. So if you try any value which is bigger than 0.10, we're guaranteed to get a value for q which is smaller than what we have now. That's what this thing is telling you. Let it talk to you. So we're going to try a value for x that's a little bit smaller. And I'm going to tell you right now, try this. Now the arithmetic is not difficult to do. You now know how to play the game. This being our first example of how to play the game. And if you try 0.90, you will get Q equals 1.017. So I say you got to cheat on these significant figures until you get it right. Well, if I stretch this to 4 sig figs, in order to be able to get the right answer, I see this is a little bit bigger than k. So if this isn't the right answer, because to 2 sig figs this is 1.0. But be careful about stopping here, because this is still a little bigger than k. So the only other possible value, if this isn't correct, is, if this is not correct, what's got to be the other, what's got to be the correct value for x, if this is not correct? Remember, as x gets bigger, this term gets smaller. As x gets smaller, this term gets bigger. So we now got a value for x which gives us a value for this term which is a little bit bigger than k if we stretch significant figures. So if 0.90 is not the correct value for x, what is the correct value for x? 0.091. Do you agree this is ever so slightly bigger than this? Which means this term is going to be ever so slightly smaller. And with this, when you do the arithmetic, you find out that's what you get. And both of these values, this as well as this, are each what to 2 sig figs? 1.0. Which one is correct? Is x to 2 sig figs correctly 0.90 or 0.091? 0.090 or 0.091. You now have the information on the board which allows you to make this decision correctly. What is the correct value for x? 0.091. Why do we decide that? Well, if I take k and cheat it to 5 sig figs, I find out this is closer to this than this is, don't I? Good. There's your first illustration of how to tackle these challenging problems. By the common sense speculation method. No more, no less. Letting relationships like this talk to you, tell you what they mean. So with that, we plow into chapter 18. Now, most of you have already heard some of the stuff I'm going to talk about now, but that's okay. For the benefit of all and to maintain congruity in what we're offering, a brief review of what some of you have already heard and what some of you will hear about more extensively in the remaining Period 6 discussion class. Bronson-Lowry acid-base chemistry. Cap A, shorthand reference to acid. Cap B, shorthand reference to base. Is chemistry important? Yes. You remember our conversation just a short while ago indicating to you why this is so important? Because just about every solute in water solution has an existence that depends on pH. And that's what this chemistry is all about. Have you ever heard about an unhealthy physiological condition called acidosis? Alkalosis? Have you ever heard about buffers? What's a buffer? You've investigated these with your work in laboratory, so you ought to have a doggone good idea what a buffer is. What's a buffer? Well, it's a Bronson-Lowry acid-base system that is designed to do what? Resist pH change, or if you prefer, maintain pH. Any important buffers in the human system? How about blood? Is blood a human buffer system? How about tears? Tears buffer human buffer system? Sweat? Urine? These are all examples of important human buffer systems. Blood is a bicarbonate-carbonate buffer. Buffering at about 7.4 ideally. Blood pH in the range of 7.2 to 7.6, you're fine. But if you get lower than 7.2, you have what's called as acidosis. And if you get above 7.6, you have what's called as alkalosis. Just for fun. Any of you remember watching a movie that was about this? A movie about this blood pH. Didn't any of you see the Andromeda Strain? Never saw the Andromeda Strain? Well, I didn't think I was that old. But it's an interesting movie. Alien organism is beginning to take over all of Earth. Well, that's the way these stories are always constructed, aren't they? And is discovered by the scientists investigating this that all the people in the community where the alien organism came to Earth are dead, except two people. A little baby and a drunkard. The little baby's crying all the time because the little baby's sick and has a condition called acidosis. The drunkard has unfortunately been consuming sterno products, which is basic. So the drunkard's got alkalosis. These two people are not affected by the Andromeda strain, because what the scientists ultimately discover is that if pH conditions are created that are outside the range of about 7.2 to 7.6, the Andromeda strain is wiped out. And of course, that's how Earth survives. Bronsted Lowry acid, H plus giver. To this day, with all the fancy technology we got, if you want to find a material to be a Bronsted acid or base, you take it to the laboratory and make a water solution thereof. And investigate pH, no more, no less. With absolutely pure deionized water showing a pH of 7.0 or 7.00 to two significant figures under normal lab conditions. If the pH of the resulting solution is less than 7.00, the stuff you dissolved is a Bronsted acid because it reacted with water to create hydronium ion. So it reacted by giving H plus to water. On the other hand, if the solution is observed to have a pH above 7.00, then the stuff which you dissolved in water is a Bronsted base because it reacted with water to create hydroxide ion. It reached over to a water molecule and said, ripping away an H plus. And that's the way we still find out today if a material in water solution is a Bronsted Lowry acid or base. And since all the chemistry we're going to discuss is in water solution, this is an important definition to us. Bronsted Lowry acid base reaction. Take a look at the reaction equation, if you have such available. And if you can recognize by formulas for products and reactants that H plus exchange has occurred, that's a Bronsted Lowry acid base reaction. Also, if you examine the equation for any Bronsted Lowry acid base reaction, like this, or any one of a myriad of Bronsted Lowry acid base reaction equations we're going to look at in Chapter 18, you'll recognize at a glance. Now, one of the reacting materials reacts as an H plus giver. The other reacting material reacts as the H plus taker. Reacting acid with a reacting base. To create different acid and different base as products. Because whenever you protonate a Bronsted base, you've turned it into a Bronsted acid. It might still be able to behave as a Bronsted base, but at the minimum, it's now been turned into a Bronsted acid. And whenever you deprotonate a Bronsted acid, you've turned it into a Bronsted base. It might still be a Bronsted acid, but at the minimum, it's now also a Bronsted base. When we meet next week, I will have available for you a bunch of handout information regarding acids and bases that we will deal with commonly and stuff like that. We'll talk about that at that time. But back to this. Simplest acid-base reaction for us, given that all our chemistry is going to be considered in water solution, is water itself reacting with water itself. One of the waters, we don't know which one behaves as an H plus giver, the other one behaves as an H plus taker, and in so doing, when you protonate water, you get hydronium ion and hydroxide ion when you take away H plus from water. You've seen this. Nothing fancy about this. Another example. We've already looked at this example. In an earlier conversation, we talked about the fact that in hydrochloric acid solution, say, at concentrations usually encountered in the laboratory, like 1 molar or less concentrated, this is not an equilibrium reaction. This goes 100%. But so what? It's a Bronsted Lowry acid-base reaction. This stuff gives away H plus, the reacting Bronsted acid, to water, the reacting Bronsted base, to again make hydronium ion as the product Bronsted acid, because once again, water behaving as a base collected H plus. And this time you deprotonated the HCl molecule and turned it into chloride ion. That leads to language. Language which I attempted to introduce you to in 2045 laboratory. Language which applies to oxidizers and reducers. Do you remember that? Conjugate oxidizer, conjugate reducer. When an oxidizer does its thing, it turns into its own conjugate reducer. And when a reducer does its thing, it turns itself into its own conjugate oxidizer. Same thing here. When a Bronsted acid reacts, given that it reacts by H plus loss, it becomes its conjugate base. And when a Bronsted base reacts by H plus capture, it becomes its conjugate acid. So this tells us That hydronium ion, the conjugate acid of water. Or if you want to say it the other way, water is the conjugate base of hydronium ion. Hydroxide ion is the conjugate acid, conjugate base, Cb of water. Or if you want to say it, water is the conjugate acid of hydroxide ion. You can read it either way, it doesn't make any difference. Chloride ion is the conjugate base, Cb of HCl. Or HCl is the conjugate acid of chloride ion. So what's the difference between any bronze-telluric acid-base conjugate pair? H plus in composition, that's all there is to it. So with that, and many of you already have looked at this, we go to the first question in chapter 18, which is about this stuff. Hydroxopentaquomagnesium ion. I don't care about its name. Because far more important than the name of any chemical material is its formula. Formula means more. The task put before you, which many of you have already wrestled with, but I think it serves well the purpose of driving this stuff home, is for this formula, which is a formula for a stuff that you folks will in fact prepare in assignment 4 in 46 laboratory when you do chemistry of magnesium ion in water solution. Ca of this, Cb of this. Write the formulas in response to these questions on your paper. Write those formulas on your paper right now. How many of you fielded this question successfully earlier today? Remember, I asked for those of you who fielded it successfully. Not seeing many hands. Now then, what's at issue here? What's at issue is to recognize that to write the formula for the conjugate acid of this, I need to do what to this formula? I want to write the formula for the conjugate acid of this. So what do I have to do to this formula? Material-wise. Add H plus. If I want to write the formula for conjugate base of this, I got to subtract H plus. Well, how am I going to do this? Let's show you a picture. Perhaps you saw this picture earlier. This is a canted square. Canted means this square is not in the plane of the drawing surface. It's perpendicular to the drawing surface. This part of the square is sticking out here, and this part of the square is sticking behind the drawing surface. It's like taking this square and holding it this way. That's what this picture means. In the middle is magnesium ion. And up above magnesium ion, and down below the magnesium ion, we also have groups. Now, the formula is showing us that one of these groups bonded to the magnesium ion in the center of this picture is hydroxide ion. Because we're letting that formula talk to us. It's a magnesium ion which in forming this ion has reacted with 5 water molecules and 1 hydroxide ion. The nature of the interaction is Lewis acid-base chemistry. The formation of a coordinate covalent bond. Tell me. If you're a magnesium ion, you're all magnesium ions now. Do you have a natural electrostatic attraction for a water molecule? Do you have an even greater natural electrostatic attraction for a hydroxide ion? Why? If you're a magnesium ion, why do water molecules tend to stick to you? Are the water molecules not dipolar? What does dipolar mean? You did all this stuff in 2045. But I already told you, I know what goes on in that class. Or I should say what doesn't go on. That's really the sad part. Why should you as a magnesium ion and me, the water molecule, have a natural attraction for each other electrostatically? Does the water molecule have a region of negative charge density? Yes. Which end of the water molecule is that? The oxygen end? Is that surprising, since oxygen is far more electronegative than hydrogen? Is that surprising, since oxygen also has associated with it 2 non-bonding electron pairs? Do you remember writing squiggle pluses and squiggle minuses to illustrate dipole moments and their positions for polar molecules? Did you do this kind of stuff in 2045? You did that. Good. Well then, this is plus, isn't it? So do you see the natural attraction which exists between the negative end of the water dipole, the oxygen atom end, and its non-bonding electron density? And magnesium ion, even more so with hydroxide ion, because this has got a formal minus charge on oxygen atom, so you got a natural attraction here too. And what is taking place is magnesium ion in water solution has interacted, at least in creating this formula, with 5 water molecules to form 5 magnesium ion water molecule coordinate covalent bonds and 1 magnesium ion hydroxide ion coordinate covalent bonds. Now, why in writing this formula have I written the formula for the water molecule like this and written the formula for the hydroxide ion like this? Why? You see how the bonding is taking place? Because I want to write these formulas as well and as best as I can to correspond to structure, bond structure. The daggone bond is between the oxygen atom and the water molecule. So I don't give a damn about these textbooks which insist on writing this as H2O. They flunked this class. And hydroxide ion is correctly when it's an isolated species as this. We already told you about that. But when you're writing this formula, you better write the hydroxide ion like this, because the bonding is between the oxygen atom end of the hydroxide ion and the magnesium ion. This is what chemistry is all about. Corresponding to structure as best as we can. All right? So tell me, here comes H+. It's going to land on this thing and turn this thing into its conjugate acid. And even though we haven't done any acid-base chemistry yet in this class, but you have done some in 45 laboratory, I saw to it. If you're H+, which part of this complex ion, H+, are you going to land on? You land on water, hydroxide ion, or the magnesium ion? Hydroxide ion, isn't that? I bet you all know it's a better base than water, don't you? Well, if H+ lands on hydroxide ion, zip on this, what does that turn this hydroxide ion into? Water. How about that? So there is the structural formula representation for the conjugate acid of this thing. There it is. Now let's go back to the conjugate base and see how it is developed. You're now inviting this to behave as an H plus giver. Now this is a hydrogen proton. It's not a proton coming out of the nucleus of magnesium ion. We're not running any nuclear reactions in chemistry laboratory here. We don't want any of you to have the joy of going home to tell mom and dad, I did nuclear chemistry in my chemistry lab, I wiped out Alachua County, and I had one hell of a good Big Bang time. No, that ain't going to happen. So then, clearly, the only hydrogen proton potential donors that are part of this complex ion are the coordinated water molecules and the coordinated hydroxide ion. So I appeal to your horse sense. If this thing is going to lose H+, do you expect this H+ to come away from hydroxide ion or water?
Water.
Why? Why?
It's oxygen is tighter.
Why is it easier by far? Why is it easier by far to get H+ from this thing than from this thing?
Hydroxide, the oxygen in the hydroxide has like a stronger like electrical force on hydrogen.
An electrical force.
Yeah, kind of like the Coulombs, like
Tell me more about this electrical force.
well, in oxygen, there's the two hydrogen. They're also repelling each other. So the force is going to be weaker that's holding the hydrogen onto the hydroxide.
Let's be more like a chemist instead of an attorney. Do you realize the obvious similarities of this stuff to this stuff? They're each composed of oxygen and hydrogen. What's the difference? To turn this one into this one, I give this H+. Right? We just talked about that. So let's turn the tables around. I want to take H+ from this, and in so doing, I'm going to leave behind a hydroxide ion. Right? If I take H+ from this, I leave behind this. But if I take H+ from this, then I leave behind this. What's the name for this? Oxide ion. So I ask this. Oxide ion versus hydroxide ion. Oxide ion versus hydroxide ion. Which do you expect to be the far better attractor of H+ and why? Oxide ion or hydroxide ion? Want to try again?
No, I'm not going to go close.
Well, do you think attraction of positive, because that's what we're talking about, H+, do you think attraction of positive depends on effective negative charge density?
Yes.
How about that? Effective negative charge density. Now, you've all heard about material density. What's charge density? What is charge density? If I ask you to write a working definition of charge density, what will you say?
Number of charges on an atom. Charge.
Nope. Charge density. What's material density? It's mass of the object divided by its volume. What's charge density?
Charge.
Charge on the object divided by its volume. But better than volume is surface area. Because these reacting species, valence environment is on the surface. So the best way to get charge density is to take total charge and divide it by surface area. But the main difference between oxide ion and hydroxide ion is oxide ion has a total charge of 2 minus, and hydroxide ion only 1. So the correct formula for the conjugate base of this thing results from turning a water molecule into another hydroxide ion which will give you this stuff, which is a gooey white precipitate that you will prepare and study properties of in Assignment 4 laboratory. Pick it up from this point next time.